Welcome everybody to the ORCA 6.1 release event. My name is Benjamin Helmich Paris, and I would like to give you an overview over the new DFT features we have. I would like to give you now an overview of the latest CAS-DFT methods that we have developed in ORCA. So whenever you have quasi-degenerate open shell systems, like this transition metal complex here shown on the left side, and you have a quasi-degenerate ground state, you should use a multi-reference method for the description of the electronic states. Also, when you elongate or dissociate covalent bonds, multi-reference methods are needed. There are also plenty of main group elements and organic systems that behave like a stretched hydrogen molecule and have an open shell singlet ground state. For these molecules, you should also use multi-reference methods. And finally, when you're interested in excited states and you have doubly excited states in the low energy part of your spectrum, multi-reference methods are also very valuable. So the simplest multi-reference method you can think of is the complete active space self-consistent field method, CAS-SCF. In CAS-SCF, we do an expansion of the wave function in so-called configuration state functions. These configuration state functions are spin-adapted determinants. And the determinants we get by distributing a small number of active electrons amongst a small number of active orbitals in the valence region of our molecules or atoms. Once we have set up our linear CI ansatz, we minimize the expectation value of the Hamiltonian with respect to variations in the molecular orbital and CI coefficients. So in CAS-SCF, only configuration state function or determinants are included that describe excitations within the space of active orbitals. So in the CAS-SCF ansatz, we can only describe the so-called dynamic correlation if we increase our active space size. However, this is very costly because we have here this factorial scaling of the costs with respect to the number of active orbitals. The simplest approach to cover dynamic correlation is by using second-order multi-reference perturbation theory. In CAS-PD2 and FPD2, which are the most prominent examples, we calculate here a first-order correction to the wave function and then evaluate a second-order energy correction. The first-order wave function correction is expanded in these doubly excited determinants shown here on the right. There are also more accurate methods based on multi-reference configuration or multi-reference couple cluster theory. However, those methods are computationally very demanding because they are very complex and require automatic code generation. As you can see here in the figure on the right, these multi-reference couple cluster or second-order perturbation theory methods have the same scaling as their single reference analogs. However, the computational costs are much higher due to a much larger prefactor. To make calculations still feasible, another alternative would be to combine multi-reference method CAS-SCF with a single reference method DFT to account for dynamic correlation more effectively. And now I would like to give you here a small overview of the benefits of a CAS-DFT method compared to multi-reference second-order perturbation theory. So first of all, the scaling with respect to the number of active orbitals is much smaller. We only have here a fourth order scaling with CAS-DFT methods related to computing the two-body density matrix. For MRPT2, the costs grow at least with a sixth power of the number of active orbitals, which can be very problematic if you have large active spaces. For CAS-DFT, we can minimize the energy in a variational way for some of the most prominent CAS-DFT approaches, which is very beneficial if you want to calculate molecular properties. For MRPT2 is always non-variational. You need to set up a Lagrangian, which complicates the evaluation of molecular property calculation. Looking at the complexity of the energy equations, for CAS-DFT it's low to moderate, and for MRPT2 it's moderate to high. If we now look at the complexity of equations for property calculations, we can say that it's rather moderate for CAS-DFT methods. However, it can be very high for MRPT2, which is underlined here by the list of available properties that has been recently proposed, like excitation energies, NMR shieldings, and spin-spin couplings for CAS-DFT methods. For MRPT2, we basically only have nuclear gradients available. So to summarize, CAS-DFT is very beneficial for molecular properties and large active space calculations, and this is the reason why we have started pursuing the development of CAS-DFT methods. So the first CAS-DFT method I would like to talk about today is multi-configuration pair-density functional theory, MCP-DFT, which is also now available in ORCA 6.1. It starts with a normal CAS-SCF calculation, in which you minimize the energy, determine the molecular orbitals, and the CI coefficients for one or many states in a state averaging approach, for example. Then, once you have obtained the CAS-SCF solution, you can evaluate a Cohen-Sham-like energy expression. So here the energy term contains then here the nuclei, electrostatic repulsion, the one electron integrals, including here the density matrix in the molecular orbital basis that you have obtained from the previous CAS-SCF calculation. The Hartree term that contains here the contraction of the two electron integrals with two of the one-body densities and an exchange correlation term. The exchange correlation term contains the total density rho and the so-called on-top pair density, which is nothing less than a two-body density for the case that the two electrons share the same point in space. It can be easily calculated from the one and two-body density matrices from the previous CAS-SCF calculation. In MCP-DFT, we need rho and pi to get the alpha and beta densities from this formula, which holds for a single reference theory based on a single determinant. It is, though, an approximation if you use it for a multi-reference method that is based on an MCSCF expansion of the wave function. However, this trick gives us here the possibility to evaluate the exchange correlation functionals that were designed for single reference theories with the alpha and beta electron densities that we get from CAS-SCF. And if you use these alpha and beta densities to evaluate the single reference exchange correlation functionals, this is called a functional translation, and the functional preceded here by a small t. If you have a negative radicand, so the term under the square root, your density will become complex. This will never happen for a single reference determinant, however, for multi-reference methods this can happen, and this has to be handled in some way or the other. For the original translated functionals, the square root term is neglected whenever the radicand becomes zero. You can also work with complex densities for the case of a negative radicand. The functionals are then called complex translated, preceded here with a CT in front of the usual exchange correlation acronym. The second method that we have worked on and now released with ORCA 6.1 is the long-range CAS-SCF short-range DFT method. So this is a hybrid MCSCF DFT approach that is based on range separation of the two electron interactions. The long-range part of the wave function is described by CAS-SCF, which covers static correlation. Dynamic correlation, which happens when two electrons come close to each other, is described by DFT. The energy of short-range DFT then looks the following. So we use the long-range part of the Hamiltonian and calculate here the expectation value to describe the CAS-SCF part. And then we have a short-range Hartree term and a short-range exchange correlation term. So originally in short-range DFT, the exchange correlation functional, just including the short-range part, was evaluated with the spin density, but it can also now be used with the on-top pair density. These two methods, MCP-DFT and CAS-SCF short-range DFT, are also available for excited states. So if you now use MCP-DFT as an example, it's fairly easy to do an excited state calculation. First of all, you do a state average CAS-SCF calculation, and then you evaluate the state-specific MCP-DFT energy using those state-specific densities. The input for this calculation is very easy. You just have to specify the name of the functional, in this case complex translated PBE, and also specify here the name of the solver, which is TRA. I have to mention here that in ORCA 6.1, the CAS-DFT methods are just available with the second-order converter TRA. Then the only information that is required is the usual CAS-SCF input, so number of orbitals, electrons in the active space, number of roots that you want, and the multiplicity. So this approach is fairly simple, however, it can be problematic for quasi-degenerate states. And that's why we've also worked on a different approach, where an effective CI Hamiltonian is set up, computed from a linearized first-order energy expansion. In this way, we can easily handle also quasi-degenerate states, as I will show soon. The only thing that is required additionally here is to put here the CI with a dash in front of the name of the functional. Now I would like to show you here one example, which is the twist of ethylene, where we rotate the CH2 planes and change the dihedral angle from 0 till 90 and then move on to 180 degrees, which is equivalent then to the initial structure. Here we use a short-range LDA as an example and compare our methods with multi-reference CI using also here the Davidson correction. We look at the ground state, which is termed the end state, and then the singly and doubly excited states, which are termed V and Z states. As you can see here on the left, the short-range LDA agrees here qualitatively with the MRCI curve. However, there are larger deviations, and unfortunately also the difference at 90 degrees is fairly large for the ground state, but also for the two excited states. If we now use the on-top pair density for the final energy evaluation, which is then termed short range minus T LDA, we see that the curves for the excited states don't show any improvement. However, the ground state gets a little bit better and we are closer to the MRCI curve. However, we now observe here a very unpleasant artifact, which is a minimum at 90 degrees for the ground state, which is completely nonsense. If we now move to functionals that don't discard this negative irradicance and do a complex translation, we see that the excited state curves are getting much better and closer to the MRCI curves. For the ground state, we actually don't see any major improvement, which means that for the ground state, we only have a very few or no points that have complex densities, but for excited states, there are plenty of points in space that are relevant to calculate accurate exchange correlation energies. If we now move from this state average-based approach using then the state-specific densities to this effective Hamiltonian approach, we basically resemble the state-specific approach for the excited states. However, we improve here the curve for the ground state. So now with the effective Hamiltonian approach, we have again a maximum at 90 degrees and the potential energy curves look physically sound. We've also done some benchmarking, comparing various short-range DFT and MCP DFT functionals with accurate references for the TL benchmark set of 28 organic chromophores and 139 singlet transitions. So here are the best performing functionals that we have for the MCP DFT and the short-range DFT. For MCP DFT, the state average approach with the state-specific densities using the complex translated PBE functional gives here the best accuracy, which is actually fairly low. Much better accuracy is obtained with our effective Hamiltonian approach using the short-range complex translated PBE functional, which seems to be the best of all the functionals that we have implemented so far. For the TL test set, it gives a mean absolute error of 0.17 electron volt and a standard deviation of 0.75 eV, which is in the same ballpark as single and multi-reference second-order perturbation theory methods. So finally, I would like to give you here a list of available CAS-DFT features in ORCA 6.1. We have a variational MC short-range DFT implementation for the functionals short-range LDL, short-range PBE, and PBE0. We also have a variational formulation for open shell systems using the spin density formulation. We can use then for the final energy evaluation the on-top pair density for MC short-range DFT, and then we have the translated and the complex translated functionals for LDA, PBE, and PBE0. We also have the MC PDFT available for the translated and complex translated functionals LDA, PBE, and PBE0. For both CAS-DFT methods, we have an effective Hamiltonian, what we call CI approach available, which is highly recommended if you look at excited states and excited state potential energy surfaces. Both methods are available with the TRA optimizer, which is a second order approach with a step restriction. So we also looked at transition metal complexes. So there are some systems where CAS-DFT look very good, and there were some systems for which CAS-DFT look very bad, and we are currently investigating what might be the reason for that. For the future, we would like to move on and also develop fully variational MC PDFT and MC short-range PDFT methods. We would like to also transfer the developed technology from the second order optimizer to the first order optimizer, which is very popular by the people using CAS-SCF with ORCA. We would also like to develop a CAS-DFT approach using large active spaces and combine it with the approximate CAS-CI approaches, ICE, DMRG, etc., etc. And finally, we would like to move on and also compute properties, in particular nuclear gradients or properties based on linear response theory. We've also worked on new features for single reference DFT. The first one is called analytic DFT. So one problem of density functional theory as it is used today is the numeric integration of the exchange correlation energy and potentials, which is often subject to numerical noise and requires special care. Well, the obvious remedy to solve this problem is to replace the numerical integration of the exchange correlation energy by an analytical one. This is, however, not so simple, but it is possible for the Hartree-Fock-Slater method, which is one of the simplest functionals you can think of, and this is now available in ORCA 6.1. It is easily available by just typing ADFT in the keyword line of your input. And our hope is to combine that with other more accurate methods like the random phase approximation to obtain improved results without doing numerical integration for the exchange correlation energies and potentials. Speaking of the random phase approximation, we have also now an efficient implementation of the direct RPA energies. Those are usually much more accurate than MP2, and they also have a much more favorable scaling of the cost. They just scale with n to the power of 4 times logarithm of n, while MP2 has a fifth order scaling. We now have a first RI-RPA implementation available in ORCA 6, and it can be easily called by specifying the DFT RPA-C flag in the method block of the input. I would also like to show you here some benchmark results for RPA on top of PBE energies. These are results for the GMTK55 benchmark sets, including various relative energies. The green bars are RPA on top of PBE, the violet bars are the omega B97M-V functional, which is heavily parameterized and is one of the best performing DFT functionals currently available. We see that our RPA implementation gives slightly worse accuracy than the omega B97 functional. However, the results are more or less here in the same ballpark. So now I would like to give you here a brief summary again of all new DFT features in ORCA 6.1. So we have developed two new hybrid CAS-SCF DFT methods called MCP-DFT and MC-SR-DFT, which are the multi-configurational pair density functional theory and the multi-configurational short-range DFT. We put here an emphasis on excited states. There are two different approaches available. Currently, the better one is a multi-state CI-DFT approach, which also gives qualitatively correct potential surfaces. We've worked on density functional theory without numerical integration. This is currently available for the Hartree-Fock-Slater exchange method. And also, we have now an RI-based implementation of the random phase approximation for energies. So finally, I would like to give you here a list of the people who contributed to these projects. So I hope you are all excited using the new CAS-DFT features in ORCA 6.1. We are always available to hear your opinion and open to any suggestions. Thank you for your attention and have fun with ORCA 6.1. Thank you.